We've talked about how angular velocity tells me how the angle of an object, either in uniform circular motion or a rotating object, how its angle changes over time. Now I want to talk about angular acceleration. So again, I want to make an analogy with regular linear motion. And the analogy I want to make is with just our regular old acceleration. So our acceleration tells us how velocity changes over time. Now, we had talked about how that could mean speeding up or slowing down, or how it could also mean changing directions, since velocity is a vector, and the direction matters when you're talking about a vector velocity. Similarly, we have angular acceleration, which tells us how the angular velocity changes. So the angular velocity was omega. That was just telling me how much the angle changed over time. Angular velocity is going to, or excuse me, angular acceleration tells me how that angular velocity changes over time. So if I spin my wheel here, there's a certain angular velocity that the red and green dots have. If I try to speed it up during the speeding up process, there is some angular acceleration because the rate at which it's going around is increasing. I could also have an angular deceleration by just slowing those dots down so that the rate at which their angle changes gets smaller and smaller. So that's what we mean by angular acceleration. It's essentially the speeding up and slowing down of the angular velocity. So we talked about angular acceleration. But to have an acceleration, you need a force. You need a net force to have an acceleration, just based on Newton's second law, where we sum up the forces, you get the mass times the acceleration. So that would seem to imply that to have an angular acceleration, we'd also need some type of angular force. And that is in fact the case. You need a net angular force to have an angular acceleration. However, angular force is not really a term that we use. Instead, what we say is that you need a torque. So a torque is kind of like a force, but it's kind of like a force that tries to rotate an object. So what exactly is torque? You hear it a lot if you're talking about big towing vehicles. You hear advertisers say, well, this truck has a lot of torque, but what exactly does that mean? Well, I think the easiest way to describe how torque works is through an example. So let's say you have a door, and we're looking at the door from a bird's eye view, so we're looking at it from above. And you want to open this door. So here's your door. It's got two knobs on it, and then you've got some hinges here, so that the door, when you open it, is going to go this way. The door can open or close. As it's opening, it's going to swing open like this. So let's say I gave you a few different options for the force that you can apply to the door to get it to open. Say you applied a force right here by pushing on the door. You push down like this. I'm going to call this first one. And let's say I give you another option for a force. That force is right next to it. You do that one in green. I'll call that force 2. I'll give you a third option for a force. I'll do that one in yellow. You're going to be pushing this way. Force 3. We'll do one more. We'll say push, I'll do light. Push in the middle of the door right here. Force 4. Okay. So you have 4 different options. Option 1, you can push right at the doorknob with a fairly large force. Option number 2, you can push right at the doorknob with a slightly smaller force, or about half as much, I should say. Option 3, push with a fairly large force, but you're going to be pushing to the left. For option 4, you push in the middle of the door with, again, a fairly large force. Well, most of you would be able to intuit that F1 is going to be your best option. And that's 100% true. It's going to be, you want a fairly large force to open the door. But not only that, the force has to be placed in the right spot. Force 1 is better than force 4, even if they're about the same size, because it's going to be easier to open the door by pushing on it from the far end near the knob. That's actually why they put the knob near the end. You wouldn't put the knob in the middle of the door, because that would make the door harder to open. Similarly, you want to push perpendicular to, or along the direction that you want the door to move. So I want the door to be pushed, I want this end of the door to move forward. I'm going to push up like this. I'm not going to push at an angle. If I were to push at 90 degrees, the door wouldn't go anywhere. All it would do is get pushed a little bit into the hinge, and it wouldn't really move anywhere. Similarly, I don't want to push at like a 45-degree angle, because then part of my force is pushing into the hinge, which isn't going to do anything. Now, we want to be able to represent these different aspects of applying a torque to the door and getting it to rotate. So to do that, we need to account for a few things. We need to account for the force that's being applied, because bigger forces are going to cause more torque. I need to account for the direction that I'm applying the torque, or the force rather. So that direction is just going to be the angle that I'm pulling at with that force. And I want to account for where on the door I am pushing. Am I pushing further away from the hinge, which we can imagine is a pivot point, or am I pushing closer to that hinge? Where am I applying the force? So we're going to take a look at 3 different things. We're going to say that the torque depends on R, which I'm going to say is the distance to the pivot. In this case, the hinge. Theta is the angle that I pull with, or push with. I'll say the push angle. And finally, it's going to depend on how much force I actually apply. So if I'm going to get the door to rotate open, I need to push in the right spot, at the right angle, and with a certain amount of force. Let's see how the pulling angle, try it again. Let's see how the applied force, the distance to the pivot, and the pushing angle all affect how an object is going to be rotated. So again, I've got my door. Here's my pivot, which is where the hinge is. And I'm going to apply a force F. And I'm going to apply that force specifically at some angle theta. And we can adjust theta to be what we want. We could make it 90 degrees, we could make it 0 degrees. And finally, I have some distance r, which is the distance between the pivot point and the position where I apply the force. So that's just this distance right here. Well, it turns out we can define the torque to be the force times the distance to the pivot point times the sine of the angle that that pushing force gets applied at. Now, why do we write it this way? Well, if the force is bigger, we're going to have a bigger torque. So that thing that looks like a T, it's actually the Greek letter tau. That's going to be our torque. And if I have a bigger force, I have to have a bigger torque. Now, we also talked about how you want to push further away from the pivot point, so near the doorknob, rather than right near the hinge. If you push at the hinge, the door is very hard to open. Try it if you don't believe me. So the bigger the distance you are away from the pivot point is, the more torque you're going to get out. So that's why we take F times R. And then finally, we have the sine of theta. Why do we have the sine of theta? Well, I'm not going to get as much torque if I'm pulling at an angle compared to if I'm pulling at 90 degrees. If I'm pulling at an angle less than 90 degrees, some of my force gets pushed into the pivot point. Or some of the force goes into pushing the door into the pivot point, I should say. And if my angle is 0, I'm pushing the door right into the pivot point, so I'm not going to rotate it at all. I'm just going to maybe smush it a little bit. So sine theta takes care of that for us. Why does sine theta take care of that for us? Well, at 0 degrees, the sine of 0 is 0, so you get no torque. It's not going to have any angular acceleration, which is exactly what we would expect to happen if you were pulling at an angle, pulling or pushing at an angle of 0 degrees. However, if I rotate to 90 degrees, and I push up this way on the door is going to rotate up. Well, the sine of 90 is going to be the biggest that sine can be. That would give you a sine of 1. So this would be the biggest torque you could get for a given force and a given distance from the pivot point. Now there's a couple of things I should note about the torque. First of all, we've called the torque kind of like an angular force, but torque is definitely different than a force is. And it's easy to see if we just consider the units of this. So the units of force is newtons, and the units of r, which is a distance, is just going to be meters. So we can see that it doesn't even have the same, torque does not even have the same units as regular old linear force. Because torque has units of newton meters, while force has units of newtons. So they're very different things. Even though we make the analogy between torque and force, don't get confused. They do have different units. They are different quantities. But one thing that is similar about them is that they can be related by equations that are similar to Newton's second law. So one way to see that is we could say at equilibrium. So equilibrium means we don't have any acceleration or angular acceleration. At equilibrium, if I don't have any acceleration, it must be true that if I add up all of the forces, I get 0, which gives me no acceleration. However, it's also going to be true that I have to have no net torque. So when I add up all the torques, that's going to be 0. That means we have no angular acceleration, which we write by alpha. So equilibrium situations are very common in nature. So these are some problems that we're going to want to play around with for a bit, just to give us some practice working with torque.